Hi guys, in this video I'm gonna talk about a very recent but interesting paper that was released by Thinking Machine, and it talks about how you can defeat the undeterministic behavior of LLMs. Right now that the large language models are vastly used different technologies and industries, what matters the most is the fact that people used to get the result on more deterministic, while LLMs are intrinsically random, and even if you make the temperature equal to 0, you still expect some level of undeterministicity. So in this video we're gonna deep dive into this paper and talk about the main reason on how this actually happens, and they also discuss how you can make it completely deterministic with a little bit of sacrifice on the performance. So without further ado, let's jump right into it. Welcome everyone to your channel, AI Fun Fact World. For those of you who are on this channel, my name is Pedram. I have a PhD in computer science, and in this channel we talk about AI and machine learning and how we can use it in order to improve our efficiency. As you mentioned, in this video I'm going to talk about defeating non-deterministic in LLM inference. So I have a nice abstract of this in this post from OpenAI community that I'm going to discuss it and then go a little bit into detail of some of the sections and then try to wrap it up. So problem of non-determinism has been happening for a long time, and the people blame it on concurrency and floating point hypothesis. So the idea of floating point hypothesis is that we don't have the associative property when we are working with floating numbers. So what does that mean? So floating numbers are basically adaptive based on the precision that they get, and if you want to decide a specific number of digits, that can basically pretty much vary if we add two numbers of the different scale, and we can basically lose our basically precision. So let's take a look at this example. For example, 0.1 plus 1 e to the power of 20 minus 1 e to the power of 20 is equal to 0. But if you change the order and subtract this one and plus 0.1, you get 0.1. So this is something that people thought that okay, we don't know, we don't basically determine which of these basically components are going to be added together, and then for that reason it can be non-deterministic. The other reason was because of the concurrency. So the result of the weights are exits in the basically different kernels, and if they want to happen, for example, let's say in a synchronous section, we want to add all of the results together. Again, since we don't know which kernel will come first, that's where you get the non-associative property, and you don't get the same result. So this is actually a real phenomena, but this is not the main cause of LLM non-determinism. So this can actually, in individual operation, you can get a lot of run-to-run deterministic result, but again you don't get the same results of the LLM. In the original work, they actually showed a example in here, and they said that by Cuban they have 1,000 completion, and they set the temperature equal to 0, and they ask, tell me about Richard Feynman, and then they generate 1,000 token each time, and they see that 80 different unique completion. And the most common of these occur 78 times. So this basically means even with the temperature equal to 0, you don't get the same result. And they said that mostly the first tokens were the same, and then 103rd was the token that it was different. But so what is the main reason? So they mentioned that the reason is batch invariance. So what does that mean? That means that you can produce a slightly different numerical results depending on the size of the batch that is processed. So how it happens is when you are calling an LLM on the fly, what will happen is that in order to improve the efficiency, they try to batch the response, run the batch, and then get back the response. They're not gonna do each response at a time for the LLM. And obviously the load is different. Sometimes of the day you get a lot more requests, and sometimes it is less people are using it. And for that reason, since the batch is not deterministic, so it is going to be batch invariant, and the result that you get is going to be different. To understand this more clearly, that how batch size can actually differ the result, we can take a look at the original research in here. So they said that all MATMO implementation are run-to-run deterministic. However, they are batch invariant. So run-to-run means that if you run it again, you're gonna get the same result. So let's take a look at the example that they have. There is an unusual property that they cannot explain from a mathematical perspective. They say that matrix manipulation should be independent along every element in the batch, which is obviously true, right? It doesn't matter if I'm multiplying, for example, for 100 different requests or is it just 5 requests. Each one has to be done independently. And the other element in the batch know how large the batch should affect. So if it is 100, if it is 10,000, why would that matter? But in here we can see the result is different. So they actually provide 2 A and B matrices, and then in first they compute the torch.matmo with A, the first row, times B. So that's the first one, and then on this one they actually multiply the whole thing, so A and B for all of the rows, and at the end they just subtract and choose the first one. So if you gotta think about it, so these two are the same, the only thing is that they are done in a separate steps. If you actually compute this, you will get this huge result difference. So why is that? This is a run-to-run deterministic, which means that if you run multiple times, you always get this result, that these out one and out two are different, while it is actually doesn't make any sense. So what is happening is that the load determines the batch size that the kernel run under, and this basically creates this difference. So try it yourself and see that it actually matters if you actually choose the first row in here or in here. So that is basically the result that mainly causing this. So in order to solve this, they actually provide a solution for these three: RMS, matrix manipulation, and attention, and then mention that you're gonna sacrifice a little bit of your performance and make sure that each time the batch size is processed regardless of the number of the elements. So sometimes means that sacrifice a small performance that you get from the kernel, for example the split K or dynamic attention, and especially you cannot use those. Basically a standard VLM 80 unit computation, and if you do deterministic VLM, they actually produce only one. So this actually shows that in one task that took 26 seconds on default, it takes 42 seconds. So not exactly twice, but considerable amounts larger, because you are not doing the performance improvement. And then true on parse CRL, this is a huge benefit by ensuring that the model you use, the sampling, is bitwise identical to the model being trained. It allows train on a true on policy RL, which they show to prevent the reward collapse inside the experimentation. And there you have it, guys. We have discussed how to systematically defeat the deterministic behavior of LLM, and we saw that modern softwares contain many layers of abstraction, and when we run into non-deterministic and sudden numerical difference, it can be tempting to paper over them. So it is already probabilistic, so what's wrong with that? One might say that as long as my answer is right, why would I care that the LLM result to be exactly the same? So in some situations where the LLM actually is going to be used inside the function calling, or some of the cases we actually want complying an exact style, and the most important, if it is a long context, we want it to repeatedly provide the same result, right, and sometimes act flakiness. So that's definitely a very important result. If you enjoyed the video, make sure to like it. More importantly, subscribe to the channel. Let me know in the comments what do you guys think about this approach. They also have the code for it. You can try and see that how you get the result. I put the link of this article inside the description of the video. If you're new to AI, I suggest you to watch these 7 important buzzwords in AI that you definitely need to know. And if you're a researcher, you can look at this that I talk about the ICML papers and what has been discussed in this year ICML. Thanks for watching, and see you until the next one.